So you'll find that you'll use the frequencies command or menu in SPSS whenever you want. First of all, whenever you have categorical data, so you want to count up the number of males and females that you have, and you want to compute percentages and the percentiles, the interquartile range, 25th percentile, 75th percentile, 50th percentile, median, mode. You can get all of that from frequencies. It will also make you a histogram of that variable if it is a continuous. Well, yeah, I mean, it'll make you one as long as it's a numeric variable. There's an easier way to make a histogram that allows you to do some more stuff with it too. The second method, as you'll see in this video, is to use what's called the descriptives command. And that gives you, instead of having to click and ask for a bunch of options, it automatically just gives you a ton of information about each variable: mean and median, the variance, the standard deviation, standard error, usually the range and the skewness and the kurtosis, so that information about whether the distribution is wonky or symmetrical. To get confidence intervals, you have to use something called the explore command, which is actually often used when you want to break out your data. So for example, if we had data on blood pressure and you wanted to look at the males separately from the females, you would use that as well. And that's where you get your confidence intervals from. So you can take a look at these after class, this week. And again, I'll run through just some of the graphing things once we're done. So just uploaded this morning. I took these off. I'll put them back if you want, just some examples of normal distributions in the wild. And then, sorry, this is your presentation. This is the homework file. So you'll want to use, it's a different file, similar data set, just with fewer variables. So I stripped out all those extraneous variables so you can kind of focus on what you're supposed to be doing. So download this and that's your homework. So that's due Monday night. The quiz is due on Friday. Right. So any other questions before we get started? Okey-doke. So there's never like a good place to kind of, transition between last week, this week, and the next week. So I'm sort of trying my best. So what we're going to do this week is really, we're going to talk a lot about probability and to ramp ourselves up to next week, but also give you some information about this week. The SPSS homework is really more about descriptive statistics, which, we don't talk about very much. We assume that, you know that, or, just suffice to say, if we have a sample of data, we can compute a number of different statistics numbers that tell us about it. So last week we talked a little bit about central tendency, what that is. We'll talk about it again briefly once we get to the normal distribution. And again, this is the idea that in numeric data sets, that there is the tendency for a single value to be most common and for the data to kind of clump around it. So this is especially true of variables like age, height, things like that, really pure numeric variables. In categorical data, so, male versus female, central tendency doesn't really make a lot of sense. What we do is instead just look at the frequency or proportion of our data that falls within a particular category. Now, the reason that we do these things happens to be because these sample statistics give us good estimates of what we call the population parameters. So the reason that we usually collect data at all is because we're interested in knowing some information about a large swath of people that we call the population. So I'll talk a little bit about that today and then talk more about it next week. Okay? So in order to kind of make sense of all that, right, we use probability theory. So probability theory, again, is sort of a branch of mathematics in which we study events and try to put a measurement on events, probability, that indicates how likely they are to happen. So in this course, we're going to be first focused on 4 special distributions that Dr. George has good notes on in the text you can read about. So it's the Bernoulli, binomial, and Poisson. These are discrete distributions because the variables that they pertain to discrete random variables. The normal distribution is the main continuous one we're going to talk about, although we're going to add some more in the following weeks. So that word parameter, right? What that means in probability theory is if we consider, when we're studying, say, again, if we're studying blood pressure in lieu of hypertension, there is a true, and let's say we're looking at, males over the age 65, particular group, there we make the assumption that there is a true average blood pressure for that group, for that population, specific population. And we also assume that, there are these unseen things that cause individuals in that group to have blood pressures which are slightly different from the average. And so to describe that tendency in the population, we try to use a probability model. And that probability distribution is idealized. It sort of exists, but we're not really ever able to observe all of it. So we write down these things called parameters, which are usually population mean and population variance, not always, but there are things that that describe the population distribution very, very well. And generally what we do in statistics is try to come up with estimates for these things. So it turns out that the sample mean and the sample variance for a normally distributed variable are very good estimates of their population counterparts. The other thing that we want to be able to do, so that's the first place where probability is important in estimation. The second thing that we want to do in statistics is we want to make statements, probability-based statements about the things that we're interested in. So when we start to talk about statistical inference, which we'll start a little bit this week and do more next week, right? Making a statistical inference. The way that we do that is we do that probabilistically. So we use the theory of probability. We run a study and we set up, we run a study, and whether or not we set up a hypothesis is not, doesn't actually matter for this part. We run a study and we collect data, and we use those data as estimates of these population parameters. And then we use probability to make statements about, sort of how uncertain we are about whether our estimates are good or not, or how uncertain we are about our estimates in general. And that uncertainty in turn helps us test hypotheses. So that's kind of where we need to go in the next 2 weeks. Okay? So we're going to learn a little bit about probability in abstract, which is often a little bit difficult for some people, but we're going to do our best. So probability, like other areas of mathematics, starts with axioms, which are things that we assume to be true without needing any proof. So we just kind of assert that these things are what they are. So with probabilities, there's 3 foundational axioms. The first one is that we make it such that probabilities can only be 0 or greater than 0. They can't be negative, essentially. You can't have a negative probability. The other thing is that, and this number 2 sort of requires even more background, but let's just consider for a second that in any experiment or any observation that we make, we are certain to observe something, right? So again, if we, trying to understand, well, what's the probability that a male has diabetes? We observe males; they can either have diabetes or not have diabetes. The probability that they either have or don't have diabetes is 1.0. It's guaranteed to occur. That's rather trivial, but what this does, right, these two together, is basically make it such that probabilities are bound to be between 0 and 1. Right? And in that way, they operate kind of like percentages. The third axiom is really helpful when we're interested in multiple events and whether or not one of this set of multiple events occurs. And that's that if events are mutually exclusive, and I'll talk about that, what that means in a minute, the probability of any of them happening is just the sum of the individual probabilities of happening, right? And that's how we actually get number 2, right? So again, there's, let's say, a 50% or 35% chance that a randomly selected man has diabetes and a 65% chance that it doesn't, right? You can't have diabetes and not have it at the same time, which is the definition of mutual exclusivity. So if two events are mutually exclusive, it cannot happen at the same time, or they cannot be observed to be happening, together. So if we're interested in the probability that a man does or does not have diabetes, we just add together the two probabilities, the probability that they have it, 65, probability they don't, 35, and we get 1.0, which is always going to be the case. If we exhaust the entire, that's what we call the sample space or the event space. Everything that could possibly happen in our study, right? We're always, if we add them all, if they're all mutually exclusive, when we add all their probabilities together, we're always going to get 100% because something must happen in our experiment. Now, so we talked about the fact that the first two axioms, from that we can derive that probability, which is almost always going to be denoted by either a capital P or lowercase p. And we usually give X as our random variable. Sometimes we use events as we do down here. We can derive the probabilities are between 0 and 1. The next part is really helpful. So basically, we can then derive in general, without the mutual exclusivity, that if we have two events, A and B, right, the probability of one or the other happening is simply the probability of the first thing happening plus the second thing happening minus the probability that they happen together. Now, if two events are mutually exclusive, it turns out that by definition, this thing, which we'll call in a minute their joint probability they happen at the same time, for mutually exclusive events, this probability is always 0. And this statement reduces to what, this is just this part, P A or B equals P A plus P B, is simply just a mathematical form of statement 3. So let's put this into context. You're in a room with 100 people, excluding yourself. So you're in the room, but you're not one of the 100 people. You're an observer, an objective observer. So excluding you, there's 55 people with brown eyes, 35 with blue, 10 with green. No other eye colors for right now. So given what we just talked about, what is the probability that the first person that you walk up to and talk to has brown eyes or blue eyes? Think about this for a second. Here I haven't phrased it in terms of probability, but what you can do is remember that probabilities in this case can be defined as proportions of the total. So we've got 100 total people. We divide them up into these 3 groups. Right? The proportion of folks in each group is the probability, right, in this case. So try on your own to come up with the answer to this first one. Anybody want to take a stab at it?
Yeah, it's 90. Because it'd be the summation of 55 plus 35.
Right, but what do you want to do with that 90? It's not, the 90 isn't technically
90,
correct.
90%
Right.
probability.
So you got to divide 90 by 100, right? To get 0.9, which you can then turn into a percentage. That's correct, right? So the probability that somebody has brown eyes, or the proportion of brown-eyed folks, is 0.55 or 55%. Blue-eyed folks is 35 or 0.35 or 35%. So then by that, let's forget that we're forgetting two things. One, Max Scherzer, if anyone knows who that is, if you follow baseball, Max Scherzer has, I always forget the condition, but he has two different colored eyes. So if we forget him, then we would make the assumption that each of these outcomes is mutually exclusive, right? But we put this in here anyway, just to assert the fact that we can always check on mutual exclusivity by figuring that out analytically. There's other ways to do it, right? So the probability that someone has blue and brown eyes in this room, because nobody has, I forget what that's called. It's like dichromatic. It's going to bother me now. Somebody can look it up. Right? Since these two events are mutually exclusive, we can just add these two. But if we wanted to get fancy with it, oops, that should be a minus. So that would matter if the events weren't mutually exclusive, like, we're talking about eye color and hair color, right? You could have brown, blue eyes and brown hair at the same time. Okay. So where is this important? What's important is we're going to make the assumption of what we call independence amongst our sample observations and usually across studies. And in a second, we're going to talk about how events that are independent, right, their joint probabilities can be easily written down. And also when we want to, if we're interested in large swaths of a probability distribution, we can add together different probabilities to get an overall probability of some number of options, which we're going to illustrate in a little bit. This is often called the summation rule. Okay. Another sort of more important foundational probability concept is the concept of conditional probability. Conditional probability is actually what we're going to do a lot in this course without knowing it. We're actually going to be, instead of being interested in conditional probabilities, we'll be generally computing what are called conditional expectations. That's what a regression analysis is. So we'll come back to that later on, right? What is a conditional probability? A conditional probability is the answer to a question that's phrased something like this. Given the value of some variable x, so given that we know something about somebody, right? So x, again, could be eye color, right? What's the probability that another variable y, say their hair, is of a particular color? And so that's a conditional probability. What we're most interested about conditional probabilities is, first of all, if we change that value of x, does y change in a meaningful way, right? So if the person, so we can easily do this usually with the right data, right? If we compute this first part and write down the answer, but then change the value of eye color from blue to brown, and then look at hair color. If that changes in some meaningful way, we can conclude that x and y are statistically related, right? And when we generalize that, last week you made a scatter plot. Who remembers what the scatter plot illustrated from last week's homework? Anybody remember? It'd be weight and BMI, I think. Was that it?
Yeah, it was weight and BMI, or weight and height.
Oh, weight and height, right? Which, is going to be similar. Weight and BMI would be almost perfectly correlated. But anyway, what did the scatter plot tell you, Mike? Do you remember?
As height went up, weight tended to go up.
Right.
So it's kind of an upward sloping.
So in this situation, we'll say that weight is the variable we're given. So given that somebody weighs, and we'll do it just with men, let's say, or just with women, given that someone weighs 120 pounds, what's the probability that they, are, I don't know, 5'2". Let's say that probability is like 20% or something like that, 0.2. We would find that if we changed X, so if we said, well, instead of 120, if somebody weighs 150 pounds, what's the probability that they're 5'2"? We're going to find that the probability of Y is going to change. It's generally going to go down, most likely, right? So as somebody gets taller, they're less and less probable. It's less and less probable that they're short. I'm sorry, somebody gets heavier, it's less and less probable that they're short. It's still probable, but it gets less probable. So, oops, that should say, wait, I did these quickly today. Sorry about that. So some other examples, given that someone is obese, what's the probability that they're diabetic? That's a conditional probability statement. And then we could figure out if obesity and diabetes are related by either putting this person in a study in which they lose weight or considering a similar person who is healthy weight. Or considering that conditional distribution of people, is the probability of diabetic less or more? So we've already talked about these probability that two things happen at the same time. The word for that is joint probability. And we have to know what that is in order to answer questions about conditional probability. So again, the joint probability of two events is the probability that they happen together. Mutually exclusive events, by definition, have a joint probability of 0. If two events are independent, which is different from mutual exclusivity, they can occur together, but we can actually test whether or not they statistically are related to one another by computing what their joint probability should be and then comparing that with, this is called the product of their marginal probabilities. If these two things are different numbers, which they can be, so the definition of joint probability has some more stuff going on with it. So you can compute joint probability very generally, just like you can compute what we call total probability. We just need some extra stuff. We actually need the conditional probability of the two events. But statistical dependence and statistical independence, which is what correlation is all about, is really founded on joint probability. What we're going to see is that joint probability, so I'll go back to this, is a part of the computation for conditional probabilities. So let's talk about this a little bit. Essentially, what we're doing with conditional probabilities is we're kind of comparing joint probability to what we call the marginal distribution of the variable, the distribution of the variable by itself. So let's get some information. This comes from page 13 of Dr. George's text. Let's say that we saw that in our community, we went out and took stock of diabetes and obesity. We found that ignoring obesity, 10% of folks were diabetic. Okay? So we would call that the marginal probability of diabetes. Right? So without respect to any other information, right? That's the marginal distribution or the marginal probability, 10%, 0.10. 40% were classified as obese. So that would be the marginal probability of obesity. And then we have our joint probability here. 9% were both. Okay? So it's often the case that we can get a joint probability just by looking at combinations of variables. So this is pretty easy to do if we just ask people if they're diabetic and if they're obese, we can make a contingency table and get these percentages. That's not always the case with conditional probability. It can get pretty elaborate pretty quickly. It can get a little bit overwhelming. So how do we go about computing then the conditional probability of diabetes given that somebody's obese? So in the probability notation, it's kind of weird, right? Often we say conditional probability kind of backwards. We talk about what is the given or the conditioning event B, in this case, obesity. So that's the thing that we hold fixed. Right? Later, when we talk about regression, we're going to talk about fixed effects, right? Which is essentially going to be a bunch of things that we hold constant, and then we let something else vary and see what happens, right? So in a simple form, we answer this question by doing that. We essentially, what you would do in a contingency table is you would look at just the column or row that had folks that were obese in it. And then from that row, you would compute or count up the proportion of those obese folks that have diabetes. Now, a simpler way to do that, or how you really could do it, is you obtain the joint probability, which we were given. Okay? So 9% of our population is both diabetic and obese. Okay? Then we look at the marginal distribution of weight of obesity. That's 40%. Okay? So we turn that into a proportion. Okay, so here they are again as proportions. Probability of diabetes, 0.10, right? 10% of people are diabetic. Probability of obesity, 0.40, 40% are obese. And then 0.099% have both. So the computation is thus as follows, right? The probability that someone is diabetic, given that they're obese, right? So again, it's weird because the idea would be that you would first observe that someone is obese. That's the known in the situation. The diabetes part is the random variable. So we're computing a probability of diabetes given that we know something about the person, that they're obese. And again, we do that simply by taking the joint probability and dividing by the marginal. And we find that given that you're obese, the probability that you're diabetic is 0.225. Now, I want you to do something. I want you to compare this number with the probability, the marginal probability of being diabetic. So they're two different numbers. You can see that, right? What is this telling you? Think about it for a minute. This number is essentially giving us, if we know nothing about a person, we can estimate their probability that they have diabetes to be 0.10 or a 10% chance. Now, though, if we get more information about them and we know that they're obese, what happens to their chances of being diabetic? Are these greater chances than here?
It increases the probability.
Right. So with conditional probability, we can see that what we would conclude is that essentially being obese or someone's weight gives us information about their diabetes status. Here, weight has gone up, right? If we say, compare, so obese is the largest weight category. Right? So if we just assume average weight over here, or we know nothing, and then we go to obese, and the probability of diabetes goes up, then there must be a positive association between the two, right? Also, another way to see that is that the joint probability of diabetes and obesity in this sample is 0.09. Right? Now, if diabetes and obesity were statistically independent, then their joint probability should be equal to 0.10 times 0.40, which is really 4%, which is not equal to 0.9. And so that's another way that we can conclude that diabetes and obesity are statistically related. Okay? So in both cases, just by using information that we can collect and put in a contingency table, we can start to get some information about the relationship between these two variables. And conditional probability essentially is what we're doing in correlational analysis, when we look at odds ratios and chi-square, and then when we get more involved and start adding more variables, we're doing a more elaborate version of it. And usually we move from not probability, but we go to expected value. Oh, Mike got it. Thank you. Heterochrome. I didn't see this till before. Right. Heterochromia iridium. Two different eye colors. You all know who Max Scherzer is? Let's take a little detour and just make sure everybody knows who he is. Here's a good picture. It's easier to see. That's funny when it's farther away. You guys should be able to see this though. Hold on. Of course, we're recording this, which is pretty funny. But Max Scherzer, very famous pitcher. You can see it here, right? Actually can't see it as close. Oh, here he's wearing his contacts, it looks like. There we go. That's a good one. Now, apparently he does it on purpose. He doesn't, he could use his, you can, so people that, it's very rare, but people that have it often just use contacts. But I think he doesn't do it because he thinks it's intimidating or something to batters or something like that. He's a crazy guy. Anywho, okay, so we're done with the abstract probability stuff. We're going to now talk about some things that might be a little bit familiar to you. We're still going to talk about probability distributions, but we're going to put them to work for us. Right? So now what we just did in 9 slides fills entire textbooks. It gets a little bit more complicated, but that's all we need for what we're going to do. So there are 4 distributions that we need to talk about. You don't have to memorize anything about them. You just have to be familiar with them, right? The first one we talked a little bit about last time. It's called the Bernoulli distribution. It's very simple, right? It simply just gives us the 2 probabilities that go with any binary outcome. In probability land, usually these are defined in terms of being a success or not a success. Success and failure can be defined however. Success could be no disease versus disease, recovery versus not recovered. I mean, it can either be, male versus female, female versus male. All that matters is that there are 2 outcomes. When you make an observation in the world, one of 2 things can happen. The Bernoulli distribution is very simple, has 1 parameter, which is simply just the probability that we observe the one category, right? And then the probability of the other category. Since now here's where we use the axioms. Since in this case, we must observe something. So the probability of either is 1, right? The probability of the second category is 1 minus the probability of the first category. Really not a super interesting variable, but we will use it a lot because if we make our data ones and zeros in this way, and we simply compute the sample mean, that gives us an estimate of pi. Right? So pi, sometimes it's noted as p, is a parameter in this distribution. We don't know exactly what it is. It's also not 3.14. You'll see that in statistics, Greek letters are used for population parameters. Latin, our usual Roman alphabet, is used for sample statistics. Where it becomes interesting is when we start to think about a bunch of different Bernoulli observations together. Okay? And we move to what we call the binomial distribution. So imagine that we randomly pick 10 people off the street. We randomly went up to 10 people, and we asked them if they're diabetic or not. Before the experiment, let's say we were making a bet with our friend, and we were interested in whether or not 8 out of the 10 people were diabetic. So we wanted to write down, well, what's the chances of that occurring? Okay? Well, there's a special distribution that allows us to compute that without going out and actually doing the experiment. So if we make the following assumptions, we can use this distribution. The first assumption we have to make, and this is a rather strong assumption, but we make it implicitly in most of the things that we do in this course. The first assumption is abbreviated IID. The first I is for independent. The second is identically distributed. Okay, so independent observations means that these 10 people, right, that none of the 10 people can influence each other in any way, right? Which is pretty easy because you can't force someone to be diabetic. But let's just say, you know, for the like one way that they might be dependent is if they know each other. Maybe they have similar diets, right? In which case, the probability that one of them is diabetic could be related to or statistically dependent on. Right? If our observations are independent, then we can make use of a lot of the things that we're learning this week. And we implicitly make this assumption. Identically distributed means that they're drawn from the same distribution, right? Which is important. So this is the formula for a binomial distribution. And this formula will return an answer to this question if we know some things. It's a crazy looking formula. It's actually not too bad, right? If we ignore this thing at the front that we call the choose function, it's simply the pi, the Bernoulli parameter, the probability that in the population of having diabetes, pi raised to x, which is the number in question, 8, right? So in a binomial distribution, a random variable is some count or number or sum, right? So if we added up all the people that were diabetic out of 10, x is our random variable. N is a parameter of the distribution, the number of observations we can make, 10. The choose function is actually not too bad. It involves the factorial operator, which you would have learned in pre-calc or algebra, which is just a number. So if n is 10, then n factorial is 10 times 9 times 8 times 7 times 6, all the way out to 0, right? What we're essentially doing is we're making use of the multiplication rule for joint probabilities. So we're multiplying together 8 of the diabetic probabilities with the rest 2 of the non-diabetic probabilities. And then this part, the choose function, just tells us how many different ways we could have gotten 8 out of 10 diabetics. So a couple things about the binomial distribution that are important. First of all, it has 2 parameters. We always need to know the total number of trials performed, which is often when we use it, the sample size. So if we have 100 people in a study, okay, and we're interested in, again, a binomial outcome, diabetes, no diabetes, then N is going to be just the total number of people, because each person represents a trial, a chance to observe whether or not someone is diabetic. Pi is the probability in observing each person, the probability that that thing occurs, diabetes happens. So in the binomial distribution, the random variable is a number of successes, or a number of times one of the outcomes of interest occurs. It can be shown that then the average or expected value of a binomial variable is simply n, the total number or sample size, times pi, the probability that any one observation is in the one category. We can also compute the variance. Okay? So here's an example where the population parameters are n and pi, but that's not the mean and variance. The mean and variance of the distribution are functions of that. So the mean of a binomial distribution is n times pi. Its variance is n times pi times 1 minus pi. So that's a lots of fancy math. Let's put it to use. The way we compute this is as follows. Right? With pi equal 0.1, so again, we'll go back to the 10% probability of diabetes in the population. Right? The choose function, you can do that on your calculator, or there's many, many different calculators that or online you can do it, right? 10 choose 8 turns out to be there's 45 different ways to get 8 things out of a total of 10. This part is a very small number, right? 0.001. And then the last part, 1 minus a 0.9, 1 minus 0.1 to the basically squared is 0.81. We multiply all these things together and we get a very low number. Okay. Why is it so low? Think about this for a minute. Think about the question we're asking. We're asking whether or not 8 out of 10 people would be diabetic if in the population, what does this number tell us? If we put it in terms of out of 10. Diabetes has a prevalence of 10%. What does that mean? If we get 10 people together, how many of those 10 people should have diabetes if prevalence is 10%?
Should be 1.
1 out of 10, right? That's the expected value, right? If we simply take this pi and multiply by n, it's 1. Here we're asking, well, what about 8 out of 10 people? Well, it's very, very low because this is very unlikely given what the background information is. Right? So we can, the mean is 1, right? The expected value in this case is 1. Variance is 0.9. So again, variance gives us some measure of fluctuation. Right? It's not very large in this case relative to the mean. The standard deviation is even more helpful, right? So we could say that if we were going to do this experiment where we looked at 10 people and wanted to know how many of them would be diabetic, our best guess is that one of them would be diabetic. The standard deviation tells us that we'd be off by about 1. So because the binomial distribution is discrete, it's only defined at these what we call points. which are the outcomes of our experiment. So if we have 10 people that if our sample size is 10, there's 11 outcomes, right? Because certainly we can observe that 0 out of the 10 have diabetes. Okay? What's the deal with this distribution? Skewed, right? The reason it's skewed has to do with pi, right? Pi is very low, right? So the probability of being diabetic is quite low, such that the total number of diabetics out of any n, right, is generally going to be estimated to be low. So most of the probability, what we call the probability mass, in this type of binomial distribution is centered around the expected value, and that which is towards one side. And then as we get further and further away from that, probability drops. Now, if in the population, pi is a coin flip, essentially, is 50-50, we get this nice symmetrical distribution here, which actually should go from 0 to 10, not 1 to 11. Sorry about that. So the binomial distribution, so this is important. Binomial distribution is symmetrical if pi, the probability of the event happening on any single trial, is 0.5. For any other number of pi or p, the distribution is going to be skewed. Low p's mean a right positive skew, high p's mean a left negative skew. Now, the binomial distribution is pretty difficult to use, especially once you get, once n becomes any number, greater than like 15 or 20. You essentially have very large numbers here and very small numbers here. Okay? A really cool thing, though, happens as we increase n. Okay? Let's take a look at this. This is a binomial distribution where n equals 50 and pi is 0.5. Does this look familiar to you, this shape?
It's a normal distribution.
It looks very bell-shaped, doesn't it? It looks like our old friend, a normal distribution. And in fact, there's a really cool theorem. Well, it's not even a theorem. I think it's just a result in probability theory that shows that as sample size continues to increase, the binomial distribution converges to the normal distribution. Why that's important is because, as we're going to see in a little bit, the probabilities on the normal distribution are easily obtained. Before there were computers, people worked them out, and they're just a little bit easier to get than binomial probabilities. But this is also very helpful just in general for answering these probability questions and also doing tests on proportions, which we'll learn about later in the course. Okay? Another thing I want to talk about is the difference in probability between what we call either the mass or the density function, which we see here, which usually has a hump, which gives for each value of the variable its probability of occurrence, and something called a cumulative distribution, which we can also visualize, but is simply, you can think of it here as, so a cumulative distribution is often defined at a particular point and below. So let's take it x equals 30 here. The probability mass function is, for x equals 30, approximately 0.04. What we call the cumulative distribution function, the probability that we would observe any x that's 30 or less, is much larger. It's obtained by adding up all of the probabilities below that point. We're going to put this to use when we get to the normal distribution in a little bit. So sort of what we care about with the binomial distribution is, first of all, it's got these two parameters, n and pi. The expected value of a binomial variable is just n times pi. And that it's a very good model when we're interested in a number of events falling into one of a binary category out of some total number. Right? So we will use the binomial distribution a lot when we get to logistic regression later on in the course. Okay. I want to mention the Poisson distribution, and I apologize because the question already appeared on the homework, and I think everybody got it right. But the Poisson distribution we'll talk about when we get to talk about what we call count regression. So we're oftentimes interested not in some proportion out of the total events happening, but we are usually interested, well, not usually, but sometimes we're interested in population health. It is often, some number of patients that arrive at a primary care practice or at the emergency department or something like that. The Poisson distribution is an excellent model for some number of events happening within a specific unit time. Okay? And it has one parameter, lambda, which is its mean, and also its variance. And lambda is related to something we call the rate of the Poisson process. Okay? So if a Poisson distribution has a high rate, then lots of events are likely to occur in a given time. If it has a low rate, then not a lot of events are likely to occur. Here is an illustration of a Poisson distribution for lambda equals 3, so mean and variance equal 3. Now, this looks a lot like a binomial distribution, doesn't it? A skewed binomial. In fact, it is. A Poisson distribution is essentially a generalization of the binomial distribution for rare events. One place where they're different is the binomial distribution is defined only for n discrete outcomes, whereas a Poisson distribution is technically defined for an infinite number of positive or zero outcomes. Okay, so it's tiny little difference, not important for us. Okay, so this is where this is going to become important. Is we're going to learn about how to use what we call count regression or Poisson regression later out in the course. Because we might be interested in, well, if we, if it's nighttime and we put this quality intervention in place, does that decrease the number of, non-essential ED visits that we get in, 30 days time or something like that, right? Okay, so now to our friend, the normal distribution. The normal distribution is really the most important, probably the most important distribution, not just continuous distribution in probability and statistics. Whole books could be written about it, so on and so forth. Sometimes it's called the Gaussian distribution or Gaussian distribution. That's in honor of Carl Friedrich Gauss, a very famous mathematician. He, along with Simon de Laplace, sort of arrived at it, suggested it as a model for error in estimation. But what you can think of it as, and actually let me pause here because I think this is better if I show you the picture. You may or may not be familiar with the fact that it does have two parameters, and those two parameters are its mean and variance. We use the Greek letter mu and the Greek lowercase sigma squared, and the squared is part of the symbol. It gets confusing. People get a little confused about that, so we'll discuss that. And we often abbreviate a normal distribution as capital N, and then we put numbers for the parameters in parentheses. So this is its graph. It's an ugly looking equation that you will never have to use. there's a couple of important points about it. So let's first of all think about what it is, okay, and how it came to be. The way that it came to be is that way back in the 15 and 1600s, the biggest things that you could do in science was be an astronomer, use telescopes and the like. They were being developed. And by the 17th century, people were getting good at making observations of positions of stars and planets, so on and so forth. And it was found that, so think of it this way, right? A planet or star is generally we would consider at a fixed point in our sky, right? And over some, period of time, it's not going to move. Some they do move, but let's consider a point in time that we know it won't move. But we have a few different humans, or even just one human, taking observations of this position over successive nights, or even a few times a day. And let's say we have many different people. What we're going to find is that the observations don't all line up, right? They tend to, if we plotted their histogram, they would look sort of bell-shaped like this. And again, this very complicated formula was arrived at to get very precise. But what you can kind of think of the normal curve as is, think of something like population, BMI, or some other continuous variable, height, right? And you have to think about homogeneous groups of people. So like, again, let's say, children of, that are 36 months old that are female. Right? It's a pretty homogeneous population. Right? What we might think is that there is some true average height that a child should be at that age and point in development and that particular sex. But then there's also all of these random things, genetics, environment, all these things that kind of add together that we don't know about, that make the height a little bit different, that kind of push it in one direction or the other, right? And so when we look at height, we don't just see one spike. 36-month-old infants are not all, however long or tall, right? They vary. And they vary in this general way, that most of them are of that mean height. And then we do have some folks that are shorter and some folks that are taller, but the further away we get from the mean, the less and less likely those values are to occur. They do occur. We can get very, 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 very tall 3-year-olds and very, very short ones, or 2.5-year-olds 36 is 1.5. Oh man, I'm having some trouble. It's 2.5, isn't it? 24 months is 2. It's 3. That's 3 years old. Oof. I didn't eat enough before class. Anywho, that's sort of the thought experiment you can do for the normal curve. It was then found. So how do we make the jump from astrophysics to humans and social data? It was really in the late 1800s that was done in a couple of different places. But generally it was Darwin's cousin, who now I'm blanking on. Again, I haven't had enough to eat tonight. And I have his little machine. It's in the office. Galton, Sir Francis Galton, did a number of studies of, by that point, they were getting interested in eugenics, unfortunately. And so they're starting to measure people, different races and social backgrounds and stuff like that. And from there, you could see many, many different behavioral and physical measurements of people took this form as well, which was just sort of very interesting. Now, importantly, right, an important thing we need to learn about the normal distribution is that we can never know the probability of a specific number occurring. What we're interested in is the proportion or area under the curve between 2 points. Okay, so let's consider IQ, human intelligence quotient. what we have here is a picture of the normal distribution. And at these different points, all we've done is calculus has been performed. So the area under the curve at between any 2 points is obtainable using using integrals. So this was done years ago and appears in introductory statistics texts. And so we're going to be interested in with the normal distribution and then the t distribution, the f distribution, and the chi-square distribution. We're going to be interested in large swaths of the probability distribution. So for example, in this case, what's the probability that somebody's IQ is 132 or less? Well, just like before, it works the same way as with discrete distributions. We add up the different areas, right? Now we could compute that whole thing, but here we can estimate it as 39.59 plus 34.13 plus 34.13 all the way down. Okay? And it turns out to be fairly close to 97, about 97-ish, which is really the definition of percentile in most situations. So most percentile distributions that you've heard of, so 97 percentile on IQ and height, weight, they're actually based on normal distribution curves like this. All right. So I think that's a good place to take a break. We've made it through a good amount of stuff already tonight, so that's good. So let's take a little break. I'll get some more sugar, and then we'll resume at 6:37. Sound good? Okay, cool. So, yeah, we really blazed through a lot. So I do want to stop and kind of mention that this is not a course in mathematical statistics or anything like that, that you'd have to, compute any of the things that we're talking about. It's more just so you have familiarity with these concepts to see where they're going to come up later on. One of the things that we are going to start to talk about this week on homework is whether or not a numeric variable that we have, is it normally distributed? And the reason that we want to know that is because that's often going to be an assumption of statistical tests that we might want to run later on. So t-tests are predicated on that, analysis of variance to a certain extent, linear regression. The second place where normal distributions are important, we preview it this week on the quiz or on homework, and then we'll kind of make use of it in the next few weeks, is in this concept of what we call a sampling distribution. So the rest of tonight, we're going to try to talk about that sampling distribution. That's another pretty abstract concept that we just want to get sort of a working knowledge of right now. We don't need to be experts at it. But I sort of like to throw some of the math at you just so you see it, so it doesn't, surprise you elsewhere. And remember that, formulas in mathematics is just a language. It's just a way to kind of write down instructions. So, after this week, you won't see too many of them because we don't really use them. We let the computer do the work for us, but always do like to kind of show them to you. Okay. So a couple more notes about distribution. So one of the things that we do need to do is, as I said, we will want to consider sort of, okay, what's the probability that we would find an observation at, or say below, or at or above a particular point on a distribution like the normal. we can do that using, so all these percentages, all this stuff is obtainable because the equation essentially is only defined between the equation itself, if we add up or integrate the entire function from negative to positive infinity, it will equal 1.0 on the dot. So essentially the results of integration for the normal distribution are proportions that we can interpret as percentages. A couple other things. A normal distribution is not skewed at all. It's perfectly symmetrical. So that's one reason why we look at skew and kurtosis in descriptive statistics. Often we display it in terms of standard deviation units rather than variance. So, kind of, you have to look closely. Sometimes with a normal distribution, we talk about it in terms of its variance. Sometimes we talk about it in terms of its standard deviation. And remember, standard deviation, little sigma without the square, is the square root of variance. And so if I know the population variance, I can take the square root and get the sample variance. There is a special form of the normal distribution that's going to be really helpful to us when we learn about t-tests in week 4. So to kind of introduce it, take a look at these two graphs. These are two different normal distributions with different standard deviations. One's basically more spread out than the other. But where are they both centered? What are the means for these two distributions? So where's the peak of these two graphs? What number is it located at?
Zero.
Right. So that's kind of weird. But it turns out that this blue line represents a very special type of normal distribution, one in which the mean is 0, and really the variance is 1, but since the square root of 1 is also 1, its standard deviation is 1. And that's called the standard normal distribution, sometimes called the Z distribution, because we can turn any normally distributed score X into, we can change its scale from X being, let's say, BMI, right, which is on a scale of practically probably, very small number to about, 50, 60, maybe 90 even. And so we can change it from that scale to a scale in which the standard deviation is 1 and the mean is 0. And we do that by computing z-scores using this Z transformation formula. The reason that we do that is because the probability distribution is simpler to work with. This changes the distribution from that really ugly formula to this slightly less ugly formula. But even still, now with computers, this doesn't even matter. It's done in the background. So this was important in the 40s and 30s when computers weren't available and you literally had to do the calculus by yourself. So what was done is tables were published. It turns out what's true of the standard normal distribution is true of any other one. So what you often learn in introductory statistics is to, for example, consider the following. Let's say that, again, IQ scores are in the population, they're distributed with a mean of 100 and a standard deviation of 16. Imagine somebody told you their IQ is 132. Okay? First thing I want you to do, and I want everybody to try this, you can actually do this in your head or just with a piece of paper. If your score is 132 on an IQ test with this mean and variance, what happens here when you transform to Z? What is Z equal to? What's your Z score? Michael's got it, but everybody else think about it for a minute. So it equals 2 because 132 minus 100 is 32. 32 divided by 16 is 2. Okay. That an IQ is 2 sigma units above the mean. Okay? That's what a positive z-score means. Okay. The second thing that it means is that we can use, I mean, you can do this with 132, but it's easier with, so this is a photo, this is a scan or a screenshot of a textbook I used to use with undergrads where we teach them to do Z transformations and all that. And essentially what this is showing you is actually what's true of the standard normal distribution with a mean of 0 and a standard deviation of 1. A z-score of 2, which would be here, has 97.72% of scores below it, which means a couple of things. Right? We can say the following. We could say, for example, that the probability of going out today, randomly selecting a person, giving them an IQ test, and finding out their score was 132. Right? The probability of that happening or them having a score of lower than 132 is 0.9772, where there's a 97.72% chance of that happening. That is the definition of percentile rank, right? Which often is interchangeable with percentile. So to say that you're in the 97.72 or approximately 97th percentile of IQ means you have an IQ score of 132 or better. Really what that means is that you have a z-score of 2. Right? Now flip it around. This is how we understand IQ, this IQ as being, sort of smart or whatever, right? What's the probability or the percentage of people, that's another way to think about it, that have IQ scores above 132? Again, we'd go back to that law of probability that the whole thing is equal to 100% or 1.0.
.28%.
Something around that, right? If we've got 97.72 below, then we'd have to have about 2.28 above, right? So again, thinking about your friend being smart, what does that mean? Well, it's defined, so IQ tests are what we call norm referenced. And the way that works, a norm reference test is we define, exceptional ability by being far away from the norm being the mean. Probabilistically, you're far away if a very small proportion or there's a very small probability that you could be any smarter, right? Now, this operation of getting a result, right, let's say of an experiment, and considering the probability of getting a result that would be even more extreme, like more out into the periphery here, that's essentially what a p-value is, which we're going to discuss next week, and I'll give you more examples for that. Right? So the main reason we are interested in the normal distribution at this point, or want to jog our memories about it, is because distributions, well, itself and distributions like it are going to be how we define p-values for experimental or study results, for statistical tests. Indeed, another thing we're going to be interested in is the central 95% of a normal distribution, right? So what two numbers, so here they are on the z-scale, what we do is we need to back transform to a raw scale to find between what two numbers does 95% of the probability for this random variable lie. This is essentially analogous to what we do with confidence intervals. Oh, by the way, I should post, this is a fun little site where you can kind of plug in different values and stuff, and it makes these different pictures for you. But we're not going to get ourselves bogged down in in z-scores and all that. Again, what we're interested in is two things. One, defining sampling distributions, and then taking this forward for p-values. Okay. So before we jump to our last component, which is, again, discussing some of this, really previewing next week, right? So what we're about to discuss after this really requires sort of another whole week. And I wanted to kind of be able to give you a little preview this week and then talk about it more next week. So before we do that though, right, I've talked about these two terms before: central tendency and variability. Now we know a little bit more about probability distributions and ways to sort of quantify both of them. So generally we use the mean and variance, but there are alternatives, right? So the median is a measure of central tendency that really gives the middle of the distribution. So if a distribution is skewed, so it's not normal essentially, then the mean is going to be misleading. The median will usually give you something closer to sort of the most typical score. It literally is the 50th percentile. Okay. And indeed, in a normal distribution, the mean and the median are the same number. Okay. So in a theoretically normal distribution, the mean and the median are the same number. Okay. The mode we won't talk about much, except for we'll actually, it's basically the value at the largest frequency. It's helpful with discrete data and multimodal data, but we really won't deal with it very much. Other things we won't really deal with are sort of alternatives to the variance. So one of them is plotting out the different percentiles of the data set and looking at the difference between the 25th percentile and the 75th. So what's the number at the 25th percentile? What's at the 75th? Take their difference. It gives you something called the interquartile range, which is, again, sort of a non-parametric kind of take on variance. One thing that's important about these, I bring them up, is this week you're going to build box plots. And box plots, if you've never made one before, they don't use mean and variance, they use median and interquartile range. So I'll show you some examples of those in a little bit. One other thing I didn't discuss is generally when we compute from our sample, when we compute the variance or the standard deviation, which is just the square root of this formula. And this is true of what SPSS gives you. So this week, when you ask for descriptives and you see there'll be box for variance and standard deviation, it's computing it this way. So the definition of variance is really as the expected value of the squared difference between any random variable and its mean, right? Which would be technically 1 over n times this. Here we have 1 over n minus 1. The reason, and you can read in the text if you're really interested, I decided to just cut that content out. Sigma squared, the population formula or definitional formula for variance, is biased. So in samples where sample size is not infinite, it gives the sort of a slightly, it slightly underestimates variability. So we use this adjustment n minus 1 to compute what we call sample variance or sample standard deviation. It is a better estimate of the true population variance. Okay, so we bounced around quite a bit, but throughout last week and this week to this point, we've now basically covered, all of descriptive statistics plus probability, kind of reviewed some stuff. And so you can kind of refer back to a lot of this. What I want to do for the rest of tonight is, again, just introduce a couple of new things, briefly kind of discuss what a confidence interval is, but we're going to come back to it next week, and I'm going to give more examples because you're going to be asked to report confidence intervals on the homework this week. Next week, we're really going to dig into what they are and how do we interpret them best. And then we're going to leave p-values for next week. So again, up until this point, we talked a little bit about estimation, stuff like that, but we weren't really getting into, like, most people think of statistics and they think, well, I want to do a t-test or chi-square or, whatever. I want to test the hypothesis. I want a p-value, whatever it is. That's what we call inferential statistics, which is really what science is based on. Inferential statistics is used all over the place as well. But sort of a good definition of it, and this is what we're going to do for the rest of the course, is we collect sample data, right? Because we often don't have access to the whole population, or it would be too expensive or too risky to run a drug study with thousands of people if the drug doesn't work or whatever it is, right? So we take a sample and we use that sample, right? We compute something. And when we compute something using sample data, we call that a statistic, right? So a statistic for our purposes is a number that is computed usually as a summary of sample data. And we use that information to make statements about population parameters, about the true proportion of people that had diabetes, or the true mean, lead concentration in the blood of folks exposed to, gas from their stove or whatever it is. So in inferential statistics, I shouldn't say it's two approaches, it's two stages. They're both important. Estimation we do basically all the time. That's the process of taking information from our sample and sort of using it to give information about the population. We can then go one better, and we can sort of, before we see our data, make some guesses about what the estimation procedure will yield. Those guesses are based on something we want to test, some idea we want to test. We put it to the test, we make a decision, we move on. One very, very important point to note is that there are different types of statistical inferences. We are learning the sort of most common, what we call sort of classical inference, frequentist inference. And the idea here is we view basically probability in general as, and so our sample as being one of an infinite number of replications that could have taken place. So we define probability of our findings, because that's going to be something we're interested in for hypothesis testing. What's the probability that we would find, 3-pound difference between drug A and drug B that are supposed to be related to weight loss, right? We're going to be interested in asking probability questions about our statistics. And so we have to define the probability distribution of the sample mean or a regression coefficient, and so on and so forth. And so frequentist inference, the frequentist approach to that is to consider that our data is just, one of many data sets that we could have gotten. It's one out of a stream of things that we could have gotten. And we consider our result in light of that, all of those possibilities. So estimation and all of this really has to do with starting simple, right? First, getting information about our sample and using it to project out to the population. So a point estimate of a population parameter is a statistic that just simply returns a single number. So example, Chi-Chi computes the sample mean of 100 children in Philadelphia and uses that mean as an estimate of mu, the population level mean cognitive functioning. Right? And so we've introduced this before. This is a fancy formula for sample mean. Whatever our numbers are, right? Each X is added to all the others, and we divide by the total. We'll see in a little bit that our estimation gets better in the sense that the probability that our sample mean and our population mean are different goes to zero with large enough sample size. So point estimates are better when we have a larger sample. The real question becomes, what about, like, are we sure? Are we certain that, like, let's say we compute the mean cognitive functioning of children in Philadelphia, of 100 children, like how close do we think that is to the real? So just because we have the law of large numbers, it's great. Well, how large is large? Basically, how much are we off by is an important question. Unfortunately, in order to answer that question, we have to then think about, well, what is the distribution of sample means? Right. So now we're going like one step more abstract. Right? So again, let's consider now all of the hypothetical sets of 100 children that we could have gathered together. We've got this one, but let's think about all the infinite other ones and think about what their sample means could have been. What does that distribution look like? I'll give you a preview. Turns out that distribution, if the sample size is large enough, or if cognitive functioning is really normally distributed, in either case, large sample or underlying normally distributed variable, the distribution of sample means is also going to be normally distributed. That's helpful because it's going to help us make those certainty and uncertainty statements. So interval estimation is a sort of the goal of that. And so because of the limited nature of a sample's size, as well as sort of all the randomness that can happen. So even with a large sample, right? There's different things that occur. It's like, so again, if let's say on this test nationally, the average score is 45. Right? We would not expect, even if we were looking at, a very average set of children in Philadelphia, we would not expect their sample mean to be 45 on the dot, right? We would probably expect it to be a little bit off. So a point estimate can be a little bit misleading. It turns out we can construct an estimate that gives us a sense of our uncertainty, and that's called a confidence interval. Before we do that, what we want to do is think about and derive essentially, well, what are the properties of this distribution of sample means? Right? That's going to be a question that we need to answer in every statistic that we have. We're just going to use the sample mean to kind of work on it. Okay? So the first thing we can ask ourselves is, well, what is the expected value of a sample mean? So if I were able to do my experiment with 100 children over and over and over again, what would I expect the sample mean to be equal to? Turns out that analytically, we can prove that the expected value of any sample mean is simply mu, the population mean. Right? So all these steps are just little algebraic steps that we can do with these various operators. So if you care about that, that's great. If not, you can just believe me that a sample mean should, on average, be equal to the mean of the underlying population. Okay? Two things make that important. One, sample mean is what we call an unbiased estimator of the population mean, because its expected value is equal to the parameter that it's supposed to be estimated. Okay? That's a very important property of an estimate. The second, as I said, the weak law of large numbers is that the sample mean tends to mu as n tends towards infinity. So large samples nearly guarantee that x bar is a good estimate of mu. Another thing this tells us is that if we want to define a distribution of sample means, the mean of that distribution is the population mean. So the mean of a distribution of sample means, in order for us to quantify uncertainty of sample means, is going to be equal to the population mean. And if we don't have that, our estimate of the population mean. The second thing we need is to know, well, what's the variance of a distribution of sample means? Okay? So basically, how much should, from sample to sample, how much should that mean of 100 children's IQs, how much should that fluctuate? A lot, a little, right? Turns out, again, we can show, and you don't have to follow this, this is just all algebraic manipulation. It turns out that the variability of a sample mean, or the variance of the distribution of means, is simply the variance of the population of scores divided by the sample size. With these two things in hand, the distribution of means having mu as its expected value and sigma squared over n as its variance allows us now to quantify uncertainty in our statement, basically define the distribution, probability distribution of interest. As with standard deviation or variance of scores in our sample, whatever, we often do the same thing with variance in sampling distributions. And we give it a very special name when we take the standard deviation of the sampling distribution. We call it the standard error. In this case, it's the standard error of the mean, because that's the statistic of interest, the sample mean. Okay? In this case, it's just the square root of the variance. We found the variance to be population variance divided by n. So we take the square root of that, we absorb it into the ratio, and we get the population standard deviation divided by the square root of n. Okay? Now let's put this all together. Okay? What I've just showed you mathematically is analogous to the following fact. Okay? Let's imagine this is the normal distribution, or just any symmetrical distribution of IQ, of these cognitive functioning scores, these kids. Those are the X's, right? We've randomly sampled 100 of these X's, and they become our sample. We compute the sample mean from those 100 people. The question we want to answer is, what is the overall distribution of that sample mean? Where did that come from? Okay? So what we do is basically we say, well, we create this thing in our minds, which we would get, again, if we were to do this over and over and over again, right? Draw 100 people from the population, take their IQ scores or cognitive functioning scores, take the mean, write it down. Do it again, write it down. Do it again, write it down. Do that enough times, you can make a pretty nice looking histogram. Because the mean is just a number, right? So it now becomes our data in the next step. And so we collect data, we compute a statistic. That statistic is now data in our idealized hypothetical continuing to do that world. Right? This curve is the idealization of doing that an infinite number of times. If you notice, it's a little skinnier. You see that? The reason is, right, the two curves are centered at the same point. So the mean of this distribution is the same as the mean of the raw score population distribution, right? That's that first thing. Okay. But the variances are different. This variance is going to be smaller, and I'll show you why. So first thing I want you to do, well, we already kind of answered that, right? What's X bar? So if we take a sample of n equals 4 children from the population with a mu of 100, sigma squared of 100, so that sigma is 10, we already know X bar is going to be, what's the expected value? So what's the mean down here? It's going to be 100 also. Okay. Now I want you to answer these questions for yourselves. Okay? First, what's the standard error? So this is standard error. Here's your computation for standard error. Note the ingredients of it are up here. What's the standard error of this particular distribution? So compute standard error for how I've laid out the problem here. Okay? Then do it for a sample size of 25. Then do it for a sample size of 100. So what do we notice about this number? As sample size increases, what happens to standard error? Oops.
It goes down.
Right. So here we have 10 divided by 2 equals 5. Here we have 10 divided by 5 equals 2. Here we have 10 divided by 10 equals 1. Right? So what does this mean? Oops, I don't want to do that yet. As you increase the size of your sample, standard error gets smaller. What does that mean? It means that with larger and larger samples, this is just, again, another kind of instance of the law of large numbers, right? As sample size increases, the variance or standard deviation of your sample mean is going to get smaller, which means that the probability that your sample mean is going to be far away from the population mean also gets smaller and smaller, right? So with larger samples, X bar becomes a better and better estimate of the true population mean, such that we would expect less and less fluctuation from sample to sample when the sample size is large. Now that makes sense intuitively too, because a large sample includes more people, right? A greater representation of all of the different people that can be out there. So its sample mean is going to be more representative conceptually, and mathematically, that's written down basically in this formula. That standard error decreases as sample size increases. That's going to be true wherever we encounter standard error, and generally we're going to be encountering standard error starting in week 4. Anytime we do a t-test, which we do when we have 2 sample means that we want to compare, are they different? And also when we get into regression and examining regression coefficients. And in both cases, a larger sample size is going to be better for us in terms of accuracy of the decision that we make based on our analysis. So we'll get to that later. But that's why standard error, one place where standard error becomes important. The second place that it's important, and it's for the same reason, is in constructing confidence intervals. So, all right. So one other thing you can think of is, I always like to think of it as precision. So when we think about it in terms of estimation, an increased sample size increases the precision or decreases our uncertainty in our estimate. So one thing we haven't done is we haven't said whether or not, what type of distribution is this? How do we actually compute probability? Well, there's a really, really neat, important theorem in probability and statistics called the central limit theorem. And the central limit theorem is, really important when now we want to ask questions about sample means and other things like that, functions of sample means. It turns out that with a large enough sample size, the distribution of sample means from any underlying raw score distribution converges to the normal distribution. So why is this important? This is important because if we have a large enough sample size, generally greater than 30 for our sample, it doesn't matter if the histogram of that sample is skewed. It doesn't matter what that sample looks like. As long as it's numbers, we can use the normal distribution for dealing with its properties of the sample mean. If we have small samples, we can still use the normal distribution. The sampling distribution of the mean is still normal, but we have to make sure, we have to look at histogram, we have to do other things to make sure that it's true that these observations are drawn from a normal distribution. So now putting it all together, z-scores with standard error, with everything else, okay? Let's see how this works, okay? Let our individual x's each be different test scores from 100 children from the general population. Turns out on this test, the mean is 100. Variance is also 100. Since we have greater than 30 children, we can assume that the sample mean is also normal, with a mean equal to the population mean and a variance equal to 1, because that's the population variance divided by n, 100. Standard error is also equal to 1, because if we take the square root of this, we get 1. Because x has a normal distribution, we can compute x bar, we can compute its z-score too, and do the same thing we did before with a single score, now with our sample mean. We can standardize it. Right? So let's say that our sample mean is 98. Right? So the 100 children from Philly, we average their scores and we get 98. With the normal distribution, we can't arrive at, well, what's the probability of 98 of that? So we have to define an interval. So what we're going to be interested in is, what's the probability that a sample mean would be less than or equal to 98 in the general population? The way we do that is we just convert 98 to a z-score. So 98 minus 100 over 1 is -2. And this probability is simply the tail probability for this particular z-score. So that, again, that's found using the normal curve or a table or whatever else. We'd call this a lower tail p-value. This is a p-value, and we're going to see it next week more in action. Start to get used to it. So where the central limit theorem really helps us out is we can use it. It allows us to use the standard normal distribution as a probability model for a sample mean, which is very powerful, as we'll see next week. The next thing it does is we get back to the question we asked before. What is our, how confident are we, or how uncertain are we about our estimate? Okay? So again, point estimates don't convey uncertainty. We already saw that the larger the sample size, the more certain we can be in our point estimate. So a way to kind of convey how certain or uncertain we are about our sample statistics in vis-a-vis the population parameters is to compute an interval estimate. Confidence intervals are really great, but they have suffered throughout the ages from people not understanding how to interpret them. Right? They are not probability statements. They're intervals that are calibrated to have a certain amount of precision based on probability, but they themselves are not probability statements. So basically, the way we arrive at confidence intervals is we take the z-score formula for a sample mean. We figure out that, so let's say we know that for a standard normal distribution, 95% of the probability lies between these 2 points. Let's switch this around and figure out on our scale of our sample mean, what do these 2 points correspond to? Such that on the scale of our measurement, we're trapping 95% of the distribution of sample means. If this interval is wide, we don't have a lot of precision. Our confidence in our estimate is low. If this interval is narrow, then our estimate is very precise. And that's really all it does for us. This is, again, I'm going to go through it fast because we're going to talk about it next week a little bit more. For those who are interested in, this is how we go from that statement to the bottom statement. And the bottom statement is how we construct a confidence interval using normal theory. The way we do that is we take our sample mean to get the top end of the interval. We add to it 1.96, which just comes from the z distribution, times this thing, which is our standard error. Only thing I think I really care for you to know at this point is, again, look at the role that standard error plays. Okay? If standard error is small number, so let's say standard error is like 0.1, and our X bar is 98. That means that our confidence interval is not going to be very wide. It's going to be pretty closely, tightly wrapped around our point estimate. If standard error is really big, then our interval is going to be really wide. It's not going to be real tight and precise around our point estimate. So we're going to be less confident, or it just basically displays more uncertainty. So standard error, when it's small, our confidence intervals are going to be nice and tight, relaying the fact that our estimate is not very, very variable. And we have pretty good information about it. Again, we see that n, our sample size, is in this formula, which again illustrates for larger samples, we can expect tighter confidence intervals. We can be more confident in our point estimate with a larger sample. Again, because we have more information, so on and so forth. Okay? So at this point, you're going to ask SPSS to compute confidence intervals for you. I want you to just notice, and you're just going to have to report them on the homework. You're going to have to, I think you have to interpret them a little bit, but this part, you don't have to compute them. SPSS does it for you. Right? What I do want you to notice is, compared to the sample mean, how wide are they? Are they nice and tight, indicating we have, you know, a pretty precise estimate? We've got a lot of information in our sample, and we're pretty sure, or are they really wide? Next week, for next week's reading, you're going to read about all the confusion that confidence intervals have caused over the years. So here's some things that it is and isn't. Okay? People always get this wrong. The width of a confidence interval is set before we compute it. So the probability part of the confidence interval is fixed before we compute it. So it itself is not a probability distribution. Our population parameter is either in the interval or not. A lot of people are tempted to say there's a 95% chance that the population mean is in this interval. That's not true. Right? It's either in there or not. Right? So confidence is not the same as probability. A couple of good interpretations, you can just call it a plausible range of values for the parameter. And again, its width represents the precision of the methodology itself. So when you're interpreting confidence intervals, do not use percent chance. Do not talk about the probability of anything being in the interval. What you want to say is basically we can be this percent confident that the true parameter is in this range. Or that, we have 95% confidence in this plausible range of values. So it's a bummer that we can't use the probabilistic interpretation. It turns out with Bayesian statistics, Bayesian inference, you can do that. It's just a little bit more of a process, and we're not most of the world of science that you guys will interact with is not going to go that use that method. You can also read in the text a couple of other things that relate to the width of a confidence interval. So as n increases, standard error is going to decrease, and the width of the interval is going to decrease. All things held the same, variability in the scores in the population is going to lead to increases in standard error and increases in the confidence interval. We can also widen or shorten our intervals just by picking a different confidence coefficient. So 0.95 or the 95% confidence interval is going to be our default. Some people sometimes use 0.99, 0.90. That doesn't so much matter. But as you increase the confidence coefficient, you increase the width. Right? So to be 99% sure of something versus 95% sure, you're going to include more stuff. Right? That's the idea there. Okay. Wow. All right. So we got through all of that in 2+ hours. Is pretty good. There's a lot of information. I understand that. And again, the idea this week is just sharing this with you so that so that we have some ingredients for the remainder of the course. The homework is largely going to be descriptive statistics, a couple of questions about standard error. You already got one, essentially, I think, last week by accident. Sorry about that. But the any conceptual questions will be very, very simple. Same thing on the quiz. And in fact, the weekly readiness quiz you can usually do very well if you just read Dr. George's text, which this is probably the longest reading is this week, chapters 2 and 3. There's a lot in there, so this kind of gives you a roadmap through them. So one thing I do want to show you, I do want to quickly show you a couple of things about the homework this week. Oops. Oops, wrong one. Here we go. I'm going to share my whole screen so you can see all the menus, and it kind of makes things a little bit smaller, but that's how SPSS has decided to do things. Okay. So for homework, you're going to be dealing with the same data set, more people, and oops, I was going to share the whole screen. More people, but we got rid of all those extraneous variables. I wanted you to see the data set that way last week, because that's what a real data set's often going to look like. You're going to have to page through it and all that. From here on in, the data sets are going to look a lot more like this, so a little bit easier to manage. For homework, you're going to be doing a lot with the BMI variable, but we've got a few others. So real quick, I just want to show you, and again, there's videos on this, that frequencies, descriptives, and explore, that's where you're going to want to, you could get different things from each one. Okay? Since we were just, descriptives is easy. What you do there is any numeric variable, so you've got age, actually they're all numeric here, age, total kids, weight without shoes, BMI, height. I can press shift, select, move them all over. I do have some options here, so I'll get variance, standard error, skewness, kurtosis. Oops. And they all pop up in a list with the different columns showing you the different values. Okay, standard error is in there, as you can see. Whereas explore and frequencies, they're going to look different. So I want to show you explore because you've seen frequencies. Explore is really the most helpful when we have a factor like sex, right? And we want to get means of the different sexes and so forth. I'm not going to show you that. I'm just going to put one variable in there, weight without shoes, in the dependent list. So when we want to get descriptive statistics from a variable using explore, we use the dependent list. Now note, if I click statistics, I don't have any options other than to adjust the confidence interval because it's going to give me a lot by default. So you don't even have to do that. In plots, I can, you don't want the stem and leaf, it's old and annoying, but you can get a histogram this way. Continue and press OK. And here I've got my confidence interval. So now you could find this out, right? We get, so the mean weight without shoes across everybody is 179.2. The standard error of the mean is simply the standard deviation here, 44.121, divided by the square root of the sample size, 83.1. And to convince you, I'll show you that. We just learned that. Now it's going to be a little off with rounding error, but you'll see standard error isn't a magic trick. It's based on the formulas. So standard deviation, 44.121 divided by the square root 831. Okay. And yeah, we're pretty much on the dot. The lower limit of the confidence interval is 1.96 times standard error minus, whoops, sorry, it's really the mean, 179.20 minus 1.96 times this standard error, 176.2. We call that the lower bound or lower limit of the confidence interval. The upper bound equals, again, the mean, 179.2, plus this time, because we're going in the other direction, 1.96 times standard error. If I was change standard error, if standard error was smaller, right? Confidence interval is going to start to converge on my statistic. Until I get a very precise estimate. And then you get all kinds of other stuff. You get the interquartile range, minimum and maximum, and then the histogram. The histogram for weight's going to look a little bit funky here because it includes men and women. So it doesn't look very normal. Right? And in fact, it is skewed because we do have a few folks who are very much on the high end there. So it's a little bit skewed, but generally we would treat weight as a normally distributed variable. Okay, there's another way to get a histogram without using Explore, and that's by going graphs all the way down to histogram. This one's cool because you can also panel it just like you did. You can make different colors, different groups. Or excuse me, make different histograms for different groups. So we're going to do that right now. We're going to do weight without shoes, and we're going to do it as columns. In one column, we're going to see the men. The other, we're going to see the women. I'm also going to click this display a normal curve on there. So what it does is it draws what a normal distribution should look like as one way. So that's one way you can kind of see, do my data conform to normality? So we can actually see the male data slightly better than the female, a little less skew. But in each case, you can see how the peaks are a little bit too tall. So this curve here suggests that basically if my data was perfectly normally distributed, the histogram should fit really neatly under the curve. All the blue bars should be nice under the curve. So here we have a little bit of a departure from normality, probably because this is adults too. Another thing you might like to do is get, and you do have to do this for homework, is get box plots. We'll do a clustered one. Simple is easy to. Well, it's actually, I think you have to do simple for homework, so we'll do simple. All you have to do is just move the variable over. So we'll do this again with weight without shoes. We do have to group it. Okay, so you have to group it by, we'll group it by sex. So now we have males and females. So what is a box plot? The thick black line in the middle is the median. The top of the blue box is the 75th percentile. The bottom of the blue box is the 25th percentile. The whiskers, that's what they call these. So the full name for a box plot is a box and whisker plot. The whiskers go out, I forget the exact place where they go out to, but they go out pretty far into the percentile distribution, something to like 90-ish and like 1%. And then anything that's outside of the whiskers is denoted as an outlier. So one definition of outlier is simply scores that are, way, way far away from the middle 50% of the data. There's really no good, perfect definition of outlier. They're all relative. Whenever you see circles and stars on a box plot, that means we have observations that are outliers, that are far away from the mean and from the density of the data. So what box plots are helpful for is they don't show you normality, but they allow you to compare distributions without normality. So here we could see, right, whereas maybe it wasn't so clear on these graphs, and even with the means, we can see that the median weight for females is much lower than the males. In each case, we have some outliers. Indeed, sort of the person with the highest weight tends to be female, which skews the histogram and means. But here we can see that the distribution of female scores is definitely shifted down. Okay, final plot. For this, you have to go back to analyze. It's weird. There's a plot under descriptive statistics. There's two. The video shows QQ plots. The book discusses PP plots. They both basically give you the same information. Let's look at PP. So we see test distribution normal. We'll leave it as that. We can test others, but we're doing that. Then we'll do weight without shoes. So this is going to give us a graph. And I'm sorry, it's going to give us two graphs. The first one is going to look like this. You're going to have a thick black line on the diagonal. And what that line represents is a perfect match between the probability points in the data and a normal distribution. So if your data are normal, so if weight was normally distributed, all of the blue dots should fall right on that line. Any sort of non-linearity, so we see a little bit of bulbousness here, suggests departures from normality. Sometimes it's hard to see, so we have as an alternative what we call a detrended PP plot, which amplifies. So on a detrended PP plot, if we have normally distributed data, all the dots should be pretty close to horizontal. Right? If we have any of these sort of dancing big departures here, right? So what this is doing is we're zooming in on this part here, and we can see. So I would look at this and say, you know, along with the histogram, that the weight without shoes in the sample is not perfectly normally distributed. So the book describes PP plots. It talks about box plots and histograms, the Dr. George's text. And then there's videos of everything else on Canvas. And so just to remind you, here under SPSS resources, gives you some, takes you through pretty much everything there. Okay. So for homework, you can use that data set we just looked at. It's just going to be a bunch of questions, just like last week, compute this and that. A lot of stuff can be gotten by just running, like you'll run descriptives on a bunch of variables once, and you can just kind of read off stuff. Huh? All right. So that's it for tonight. We've made it through 2 weeks. That's good. And yeah, so any questions before I let you go?
Will this video be posted soon?
Yep, I'll post it by tomorrow morning.
Okay.
Okay.
Thanks.
And then next week we'll be in Alumni Hall, room 207. So we'll start at 5:15. And again, I'm not sure how the internet is in that room. It should be fine. But if you want to well, there's actually no SPSS next week. Next week is just conceptual stuff about p-values. So you won't even need that. But if you want the slides, maybe download. I'll try to get them ready before next Tuesday. Maybe download them beforehand, but 99% chance the internet works fine in that building. It's just sometimes we have weird issues in the classroom buildings.